Hello. Let's talk about solving quadratic equations using the square root method. So first let me just point out that so far we have solved quadratic equations by one way only, and that is factoring. And factoring is wonderful when it works because I think if it's possible, it's probably the easiest method to use. But sometimes, on occasion, there are easier methods, and sometimes the polynomial that we're given, or the quadratic that we're given, doesn't factor. And so we have to find other ways to solve it. So we're getting ready to go through this process of talking about other ways that we can solve quadratic equations. So if we were to start making a list right now, it would be very short. We only have factoring on there. But today we're going to add a second method, which is the square root method. Again, not every polynomial is solvable using the square root method without a lot of work, but sometimes there are polynomials, quadratics, that make this method very easy. All right, so again, we're just adding another tool to our toolbox here to just make sure that we are as efficient as possible and can just discuss the different methods that we can use. So first of all, let's talk about square roots, because again, we're getting ready to, we're starting this new chapter, and this is the beginning of the chapter, but we've never talked about what square roots are. So we've talked about perfect squares. If you've been with us long enough, you know from memory work that they're 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. Those you should all have memorized. I think actually maybe we've even gone up a little bit further than that. 169, 196, 225. I think that's where the memory work song stops. And then after that, 256, 289, 324. I always forget 19 squared, so hold on, let me say that. I think it's 361, but let me just confirm. Yeah, 361 and 400. All right, so those are the squares up to 20. Again, our memory work song stops right here, but if you weren't here for memory work, your knowledge of squares probably stops there. So anyway, we can say that 1 is a perfect square because it's 1 times 1. 4 is a perfect square because it's 4 times 4. I'm sorry, 2 times 2. 9 is a perfect square because it's 3 times 3. 16 is a perfect square because it's 4 times 4, and so forth. But what if we want to go backwards? What if we have a number like 121 and we say, since this is a perfect square, what number did I multiply by itself? And that's where we start talking about square roots. So if we're trying to go backwards to say, where did I start? We would put this symbol over top of the number, and that is called the square root symbol. There are other types of roots that we'll eventually talk about, cube roots, fourth roots, but this is the most common for our purposes and the only one we're going to talk about right now. But in general, that whole family of square roots, fourth roots, fifth roots, and so forth, that symbol right there is called the radical symbol. And so sometimes I'll call it the square root, sometimes I'll say just generally the radical. So just to clear that up. All right, so again, this symbol is the square root symbol. But in general, right, so when we're talking about other roots like cube roots, fourth roots, it's also just generally called a radical. Okay, so we use that symbol and it asks the question of, when I see that, I say it's the square root of 121, but it's asking the question, what number times itself is 121? And so the answer to that would be 11. All right, so we have that symbol, and when we see that, it's asking the question, what number times itself equals 11? Equals 121. And the answer to that question is 11. Right? Not square root of 11, because that would ask a separate question. So when we answer that question, we just say what the answer is. All right, we'll talk about simplifying radicals later, but for right now, I just want you to A, see that that's the square root symbol, and B, how it can help us to solve equations. So again, another side break here. Let's talk about equation 2x minus 3 equals 7. We are virtually professionals on this. We've done bazillions of these. We've done way harder than this, but I just want to help us transition from this into this. And so I would say, okay, how do you solve it? And you would say back to me, well, I add 3 to both sides. And I would get 2x equals 10. And then I would say, what next? And you would say, I'm going to divide by 2. And I say, awesome. And we say x equals 5. All right, but I want to go back here and I want to ask you, why do you add 3? Why did you not subtract 3? Why did you not divide by 3? Why did you not multiply by 3? Why specifically do you choose add 3? All right, and hopefully you have some sort of idea, and the reason is because it's the inverse or the opposite operation of minus 3. So when I'm trying to undo minus 3, I have to choose its opposite operation, which is plus 3, not times 3, not divided by 3, not minus 3, but plus 3. So we would say that addition is the inverse operation of subtraction. Then we would come down here and I'd say, okay, why did you divide by 2? Why didn't you subtract 2? Why didn't you multiply by 2? Why didn't you add 2? So think about that for a second. All right, hopefully you're saying, well, I chose divide by 2 because right up here, 2 is being multiplied by x. To undo multiplied by 2, I have to divide by 2. In other words, division is the inverse operation of multiplication. And that is why when we do that, it removes that coefficient right here. That's why up here it removes that 3. All right. And also notice that we didn't just do it to one side. Again, our equality is that balance sign or the balance symbol. And in order to preserve the equality, we have to do the same thing to both sides. So I didn't just add 3 here to get rid of it. That would tip the scales. But I have to do it to both sides. Again, I have to do it to both sides here. All right, so when we start talking about squaring and square roots, we have that symbol x squared. Let's say I have x squared equals 49. And I would like to know, first of all, this is easy enough that you can just say, oh, I know that has to be 7, because I know that 7 squared is 49. That is true, but from an algebraic perspective, how do we show that that's what we're doing? Well, again, I'm not done solving an equation until I get to the point where I say x equals something. So then the thing that's holding me back from being done right here is I have this squared. So how do I remove that square? Again, how did I remove that minus 3? I did its inverse operation. How did I remove that 2? I did its inverse operation. So how do I do the inverse operation of squaring? How do I show that I'm removing that squared so that I get the answer of 7? Well, square rooting, or taking the square root more officially, is the inverse operation of squaring. That's kind of weird from what we are used to, because here the way we removed it is by including a number, right? And so we would say minus 3, we did plus 3. We didn't just say plus, we said plus 3. It's different though when we're talking about square roots and squaring. The inverse operation is just a symbol, right? So here, instead of having square root of something, it's just the square root. That operation undoes this. And when we see these two together, all right, and you don't have to draw that symbol, I tend to, just so you remember it, but when these two are paired together, they wipe each other out. Just like when I see a minus 3 and a plus 3, it wipes each other out. Just like when I see a times 2 and a divided by 2, it wipes each other out. And so here it's going to undo that operation, and so all that's going to be left is the x. But again, just like we noted over here, I can't just do it to one side because that unbalances the equation. I have to do it to both sides. And so then I would say, oh, square root of 49. Again, that asks the question, what number times itself equals 49? And we would say 7. All right, now there's one more thing that we have to add to this. And if you remember when we were solving any type of polynomial equation, we said, well, the highest exponent is going to tell us how many solutions, real and imaginary, we should expect. So we know from this we should expect 2 solutions, and right now we only have 1. And the reason for that goes back to our factoring. So let me take this again And let me, instead of trying to use the square root method, let's go back to something we're more comfortable with. And that is when we move everything over to one side and we try to factor. So I factor this and I say, hey, that's a difference of squares. Let me factor that. It would be x plus 7, x minus 7 equals 0. And I take each factor, set it equal to 0, so this is going to give me x equals negative 7, and this is going to give me x equals positive 7. Ah, interesting. We didn't get that when we took the square root, right? Because we just assumed we were talking about the positive version. But again, if I think about this, negative 7 times negative 7, well, 7 times 7 is 49, and negative times negative is positive. That is a square root of 49. Right? And so when we are in this process of using solving by taking the square root, we have to remember that we need to put a plus or minus in order to show the two solutions that we're expecting. All right? And so our answer to this would be plus or minus 7. X equals plus or minus 7. Okay, that's just a tiny intro. Then we're going to work on that page that I sent you. Right, so if you could get that out right now, and we will start solving some of these equations. Okay, so let me also make a note here that when we use solving equations, quadratic equations with square roots or with the square root method, there's a very specific type of equation we're looking for. So again, remember when we did factoring, we gave all the characteristics of when we would use GCF, when we would use difference of squares, when we would use easy general trinomial, harder general trinomial grouping. We looked for specific characteristics, and we're going to do the same thing with solving using the square root method, because we're not going to use this on just any quadratic. It's very specific. And so we would say here that if we're looking for when we can use it, it's specifically with a pure quadratic. Every time I hear pure, I think of Harry Potter. So no muggles. We've just got to be pure quadratic. So what does that look like? All right, so there are two types that we would look for. The one is incredibly obvious, where we just have an x squared in it and it's set equal to some number. All right, so that would be one type. That would be so obvious that you couldn't miss it. It's very unusual looking. It's not like our usual quadratics where we have multiple terms. We just have an x squared and a c. In that category right there, though, we could spice it up. We could say, well, I could put a coefficient up front, so maybe it's an ax squared equals c. I could also, instead of putting a coefficient, maybe have x squared plus b equals c. I could do both. I could have ax squared plus b equals c. The thing that all of them have in common, all right, so the thing that we're looking for is there's no x term. That's why we say it's a pure quadratic. It's not also linear, all right? It doesn't have that x term in it. So when we're talking about these, again, we're looking for something with no linear term. All right, so that would be no x to the first. Again, that's what makes something linear, is it's to the first power. All right, so these all should be fairly obvious to you because you're going to notice, because you're very observant, that there's no x term in here. The one that's less obvious that I need you to be more cautious about, I've kind of used up my space because I need this right here because we're going to do a couple of these problems. Let me just try and squish it in. Would be if we have something like x minus, let me say, a squared equals c. Right, you might say, Mrs. Taylor, that clearly has a linear term in there. That is not pure quadratic. But again, if I cover that up just so you can't see what's in the parentheses, it's just something squared. There's nothing that's like x minus a to the first. It's just something squared. And so even though these take on a different form than our more obvious ones, this is still a pure quadratic. And again, there are variations of this. I might have something like, I don't know, kx minus a squared equals c. All right, so I might have a coefficient in there with it. And it doesn't have to be minus a, we just tend to do minus a. It could be plus a. right? So anytime there's just a parenthesis squared and a constant on the other side, then you're going to know that that is a pure quadratic. And again, we can jazz it up. We can have x minus a squared plus b equals c. We can have some constant out here. So again, but really the thing that we're looking for is outside of a parentheses, there is no x term. All right, so that would be your clue right here. So this is just like, you know, vanilla ice cream, kind of just plain Jane. That is the most basic form of this other variation that we're looking for, but we could jazz it up. We could put sprinkles on, we could add whipped cream, whatever. There's other variations that we could have of it instead of just this plain one. So we're going to work on recognizing those, and again, we'll have more practice with those on page 139. We're going to do a couple problems on there too. All right, so let's start with numbers 2 and 4. This is the most lovely kind, where we have k squared equals some number, and it just so happens that that number is a perfect square. All right, so we're going to say, hey, I could do this by factoring. I totally could. We just saw one on the other side where we could do that, but now that I've got this new fancy tool, I'm going to use it. All right, and it also says the directions, use it by taking square roots, so we're obedient too. So let's take k squared equals 16, and I'm going to take the square root of both sides. All right, again, the reason I'm taking that is because I need to get rid of that squared, because I want to get to the point where I have k equals something. All right, I'm not there yet because I have this extra symbol. All right, and so again, this square root symbol undoes the squaring. Right, so again, I'm not going to write these all the time. You don't have to write them at all, but I just want you to remember that these two undo each other, and so all that's left is just the k. All right, and then we have square root of 16. Well, I say, oh, easy, I know that's 4. But again, remember, I'm expecting two solutions here, so I have to put plus or minus. All right, and that would be our answer. All right, let's do the same thing here. All right, so I've got a squared equals 4. I would take the square root of both sides. Again, this symbol is undone by this symbol. We're going to find the same is true about the reverse. If I have a square root and I want to get rid of it, I square it. They equally undo each other. But for right now, we're just in this position of I need to get rid of the squared, so I use the square root. I end up with a equals, and then square root of 4 is 2, and then I'm going to put the plus or minus to indicate the two solutions I'm expecting here. Okay, hopefully you're feeling okay. Let's go on and look at problems 1 and 3. Because again, you might be thinking, well, Mrs. Taylor, this is kind of cool, but I totally could just factor. I really like easy general trinomials. Why do I need to do this? Well, because sometimes we end up in a situation like this, where I would say, oh, I'm just going to continue to using my old standard, where I'm going to bring that 76 over to the other side, and then I'm going to try to factor. But we look at that and we say, hold on, this is a perfect square. It's just two terms. They're separated by a minus, but that is not a perfect square. So this is not a situation where we can use difference of squares. So this is what I'm saying. Sometimes we're doing square root method because it's easy. Sometimes we're doing it because we have no choice. I cannot factor this equation right here. All right. So then I'm going to come along here and I'm going to say k squared equals 76. Sorry, it's just too tiny for me to write there. And I'm going to take the square root of both sides. All right, and so I'm going to get k equals, because again, these symbols undo each other, and then square root of 76. All right, hold on for a second. That was not on our list. We did 64 and then we skipped right to 81. 76 is not a perfect square. All right, so very soon we're going to talk about how to simplify radicals. So right now I'm just going to say just leave it like this, first of all. Second of all, this cannot be simplified, which again, you don't know the reason why, but just trust me on that this does not simplify. But just to kind of make yourself feel a little bit better, because that seems like that's so unsatisfying, this is the exact answer. Remember when we've talked about in class where we say give the exact circumference. That means leave pi in it. Don't estimate pi to be 3.14. This is the same kind of thing. This is the exact answer, as unsatisfying as it is. We could estimate it just like we estimate pi, but for this case, we're not going to estimate. For this worksheet, I don't want you to estimate. You're either going to leave it in the radical because it can't be simplified, or you will simplify it. So let's take the calculator and say what the square root is. All right, so I'm going to use this button. All right, the squared, again, squared and square root are right on top of each other because they are associated with each other. And so when I want to do the square root, I'm going to do the second button to get to that yellow square root symbol. Right, and then it's going to do the square root symbol, and it's going to open the parentheses here, and I'm going to type in 76. All right, before we do that, let's just estimate what square root of 76 is. I already gave you a little hint that before, it comes after 64 and before 81. All right, so we can say, I don't know what square root of 76 is, but I know it comes between square root of 64 and square root of 81. Square root of 64 is 8, and square root of 81 is 9. So square root of 76 is going to be somewhere between 8 and 9, and probably closer to 9 because it's closer to 81. All right, so now that you have that in your mind, we get 8.717797887. Again, this is not even the full answer. That's just because my calculator can't go any further. Right, so we're just going to round just for this one, just so that you know that square root of 76 does have a value, even though it's not a whole number value, that it does have a value. We're just going to say this could be thought of as approximately 8.7. But again, most times when we use square roots, we want the square root left in there. We want the exact answer. There are exceptions to that, but for right now, we're just going to leave it like that. Okay, so then let's take a look at number 3. So in number 3, we've got same thing. This is not a perfect square. We have to use the square root method. So we're going to take the square root of both sides. Square root of x squared is just x. And we are, again, remembering we have to put plus or minus square root of 21 to give us both our two solutions. And again, if we were to estimate this is going to be somewhere between 4 and 5. Again, the next square root that's lower than 21 is the square root of 16, that's 4. Square root of 25 is 5, and that's somewhere in between. So it's going to be somewhere between 4 and 5. Again, probably slightly closer to 5. But I'm just going to leave it like this. Oh, shoot, I just remembered. I didn't do plus or minus up here for 76. So we've got plus or minus 21. Okay, next let's scooch down to number 9. Okay, so number 9, again, is one of the variations on this original one that we talked about. And so we're going to do a couple like that. So here we have m squared plus 7 equals 88. So let's subtract. Well, again, we want to get m squared by itself first of all so we can take the square root. So our first step is going to be to subtract 7. These will cancel, so we end up with m squared equals, and 88 minus 7 is 81. Right, now we're just back to that basic one. With this being a perfect square, we're going to take the square root of both sides. We get m equals plus or minus 9. All right, number 10, same kind of thing. Instead of being just x squared equals something, we have a coefficient out front. So our first job is going to be to get the coefficient away from the x squared so that we can take the square root. All right, we're going to do that by dividing. These cancel, and I get x squared. And on this side, I get 100. All right, I take the square root of both sides. And I end up with x equals plus or minus 10. Okay, hopefully you're feeling like that's not too big of a jump from what we just did a second ago. I do want to look at one more on this before going back to 6 and 8, and that is number 14. All right, so for 14, Again, it looks similar to number 10. We have a coefficient right here. But what's going to happen is we end up with a fraction. So we get n squared equals 49 over 16. A little bit gross, but we are up for it. So we're going to take the square root of both sides. All right, square root of n squared is just n. All right, now this part might be freaking you out. You might say, I know that 49 is a perfect square. I know that 16 is a perfect square, but I don't know what the square root of 49/16 is. So let's take a little side trip. Again, we'll talk about this very soon in class. But there is a rule that says that if I have either a quotient or a product, and I take the square root of it, I can break it apart into two smaller ones. Again, this will not apply to addition and subtraction, sadly. Just like our exponent rules don't work when there's a plus or minus inside the parentheses, but it does for multiplication and division. Same thing here with square roots, that also works. So I can just break that apart into two separate ones and then take the square root of 49 and get 7, take the square root of 16 and get 4, and then I remember to put the plus or minus in front of it. All right, so don't let the fractions freak you out, unless, of course, they're not perfect squares. Then you're completely in your right to freak out about them. But when they're both perfect squares, just take the square root of each piece. All right. Okay, I want to point out to like number 6 and number 8 because you might think, oh, these look pretty good, not too bad. It looks just like this. But I need to point out something to you. These are sometimes a little bit of a trick, I guess. I'm going to start by dividing both sides by 2. And I'm going to get n squared equals negative 72. All right, now let's stop for just a second. Let's acknowledge, first of all, that 72 is not a perfect square, so that in itself might be a little bit frustrating. But let's go to an easier one. Let's say I have n squared equals negative 16. All right, well, we already did k squared equals 16, so this shouldn't be hard. But then I start to think, okay, well, it can't be positive 4 because positive 4 times positive 4 gives me positive 16. So, oh, it must be negative 4. That when I square it, I get negative 16. But hold on for just a second. Negative 4 times negative 4. Negative times negative is positive. This is actually positive 16. Huh. Okay, well, let's try something else. Let's try negative 4 times positive 4. That gives me 16. But wait a minute, that's not what it means to square something. To square something means I have to multiply it by itself. And I can't do two different numbers when I'm squaring. Right? So this is not even squaring. It gives me the 16 I want, but it's not squared. So what happens then? Well, what we're going to acknowledge is I can never square a number and get a negative as my answer. Right? So as tempting as it might be to say this is square root of negative 72, for right now, since we don't know about imaginary numbers, we're going to say, in our limited understanding of numbers, that there is no solution to this. All right, there is no way, no real number. Again, when we start talking about imaginary numbers next year, we will be able to do this. But for right now, we're going to say there is no solution. There's no real number that I can square and get negative 72. All right, same thing here. I'm going to divide both sides by 7. I get x squared equals negative 3. Not only is 3 not a perfect square, but negative 3 is never going to be the answer to a squared, to an equation where I am squaring something to get that until we get to advanced algebra and start talking about imaginary. So right now, again, we're going to say no solution. Now, let me just point out something. And I'm asking you not to fall into the trap that you just see a negative as the answer and you automatically say no solution. Because look, we had a negative 500 right here. If we were not being careful, we might say, oh, it's squared and we get a negative, therefore there is no solution. But again, we can only make that judgment call when we have x by itself. All right, so first we have to add or subtract any constants that we have. We have to divide by any coefficients we might have. Once we get to this point where we have x squared equals 100, we can say, oh, I was worried for nothing. It's totally fine. So don't make the judgment until you get x squared by itself. Okay? All right, one more thing, and that is that we need to look at a couple problems on this page, which is page 139 in your workbook. Oops, page 139 in your workbook, solving quadratic equations using the square root law. So again, these fall in that category of the second type, maybe the one that you're going to be less likely to notice as being a pure quadratic. And again, that's because it's got the parentheses and the squared, and you're looking at this and you're saying, I see a linear term. But in this case, we would say, if I cover that, what's in there, I would say, I see no linear terms outside of that squared parentheses. Right? And so what we would say is, okay, this is a pure quadratic. Not as obvious a pure quadratic, but it is. And so what we're going to do here is we're going to say the same thing. I need to get rid of this symbol because right now the p is trapped inside that parentheses. I need to get them out. Right? So I'm going to take the square root of both sides because I know that taking the square root will undo that square and hence free that p that's trapped in there. All right. So again, this symbol right here is going to undo this symbol right here. And on the left side, we're just going to end up with p minus 4. And on the right side, we've got that square root of 16, which is 4. And again, we're looking for two solutions, so we've got to put in the plus or minus 4. Now, this is another spot where you could potentially make a mistake right here. And so what we're going to do is we're going to say, hey, this equation, because there's a minus 4, actually spawns two smaller equations. The first is p minus 4 equals positive 4, and the second one is p minus 4 equals negative 4. And both of them are going to give us two different solutions. All right, we're not going to get a plus or minus 7 or 8 or whatever like we did before. We'll get two distinct solutions. So let's solve these. So in this one, I'm going to add 4 to both sides, and I end up with p equals 8. On this, I'm going to add 4 to both sides, and I'm going to end up with p equals 0. All right, so let's just check this. Again, we are not required to check anything with a squared that starts off with a squared. Again, we've talked about extraneous solutions when it comes to rational functions. We're also going to talk about that when we come to radical equations, but we're not there yet. Right now, we just had a squared equation, so there won't be any extraneous. Right now, we're just checking because we're feeling maybe a little bit like, how can I get two different solutions? Every square root law I've done so far has just had two, but they're identical numbers, right? They're just opposite signs. So let's check this. Let's do 8 first. So if I do, again, go back to the original equation, 8 minus 4 squared, is that equal to 16? Order of operations says do what's in the parentheses first. So this would end up as 4 squared. Is that equal to 16? Yes, it is. 16 is equal to 16. All right, so this one definitely works. Now we do it with p equals 0. So then I do 0 minus 4 squared. Is that equal to 16? Yep, 0 minus 4 is negative 4. Again, please put the parentheses around there. We'll spend more time talking about squaring negatives. Actually, we already have, but I'll just remind you that you need that in there in parentheses, because otherwise it looks like negative 4 squared. Since there's no parentheses, order of operations, actually, since this just looks like multiply by negative 1, order of operations would say do that first, and then we would make it negative, which is not what we want. All right, so negative 4 squared means negative 4 times negative 4, and yes, that is equal to 16. All right, so even though we get two completely different numbers, they still both are solutions to this equation. Okay, let's do the next one. All right, I'm going to take the square root of both sides. Again, whoops, no, I'm not. Crazy me. All right, first I need to get the square root or the squared by itself so that I can take the square root. Again, I can't take the square root with the plus, with the addition underneath it and use the same rules. Again, we'll talk about that more. But for right now, just please know you cannot do that. I need to subtract the 4 from both sides first. So I end up with 6x plus 2 squared equals 24. I'm going to take the square root of both sides. All right, so square root of 6x plus 2 squared, the squared and the square root undo each other, so I end up with 6x plus 2 equals plus or minus root 24. 24 is one that we can simplify. This is the first one, so if you know anything about square roots, just hold off. We will simplify that later, but for right now, I'm just going to leave it alone, just so that we can practice just the solving. All right, so again, this is going to spawn two equations. We're going to have a 6x plus 2 equals square root of 24, and 6x plus 2 equals negative square root of 24. Right, I'm going to subtract 2 from both sides. Right, I don't have a lot of room here, so I'm just going to show what I would get if I did that. All right, and you might say, why the heck did you put that first in front of the square root? Again, we kind of have a, I don't know what, a hierarchy, let's say that, a hierarchy, and square roots tend to come at the end. Again, we talked about first, if we're arranging polynomials, we do the squared term, then the x term, then the constant. We do them in a certain order, and when we involve square roots usually come to the tail end. So that's why I'm putting the negative 2 in front of it. All right, next I'm going to divide by 6, so I'm going to end up with x equals negative 2 plus square root of 24 over 6. Again, if you know anything about square roots and radicals and stuff like that, this eventually will simplify, but for right now we're just going to leave it as that. We would do the same thing for this one. Just because of space, I'm going to do both steps at once. I'm going to subtract the 2, and I'm going to divide by 6, and I'm going to get x equals negative 2 minus square root of 24 over 6 as our second solution. And ultimately what we're going to say is, because we're space savers, we're just going to say x equals negative 2 plus or minus square root of 24 over 6. And that will condense them into one location instead of having to write it twice. But for right now, we're just going to say those two separate solutions. Okay, last one. Again, I'm going to bring that 8 over to the other side. We get to do two things first before we solve, in this case, because we also have a coefficient here. So I'm going to do that. I get 441 is equal to 9 times 2m minus 3 quantity squared. I'm going to divide both sides by 9. These will cancel out. Fortunately, 9 does go into 441. That would be somewhat beastly if it didn't. So this would be 2m minus 3 squared equals 9 goes into 44 4 times, and then with 8 left over, so then this is 9. Yes, that's really awesome. Okay, then we're going to take the square root of both sides. We get 2m minus 3 equals plus or minus 7. All right, we've got our two equations then. 2m minus 3 equals positive 7, and 2m minus 3 equals negative 7. All right, let's go from here. I add 3 to both sides. I get 2m equals 10, and then I get m equals 5. Sorry, I'm really squished in here. And then I subtract, I add 3 to both sides here, and I get 2m equals negative 4, and I get m equals negative 2. I encourage you to go back and check those in there and just verify for yourself that they actually work. Again, start back at the original equation. Don't use some variation in between. Go all the way back to the beginning and put them in there. All right, and remember, follow order of operations. So do what's in the parentheses first, then square, then multiply, then add, and you should get 449. Okay, hope that was helpful to you. Bye.